Welcome to the world of science, where the mysteries of the universe meet the tranquility of sleep. Recline, curl up in a blanket, or simply close your eyes and let your mind drift along the gentle rhythm of this video. Today, we will explore a question that seems simple but is full of wonder. What is mass, really? Why does it determine every movement, every interaction, and even how the universe arranges itself? Together, we will step through invisible forces, tiny yet powerful particles, and the physical principles that shape the world around us, all presented in a gentle voice, allowing you to learn and relax at the same time. Be sure to hit subscribe and stay until the end of the video, because what you are about to discover will not only expand your understanding, but might also become a topic of fascinating conversations. Imagine you are sitting on a soft chair, closing your eyes and letting your body feel every tiny movement around you. When you lift your hand, your legs slightly bend, your muscles gently respond to the pull, and even your breath changes a little. Did you know that all these subtle reactions are the result of an invisible force we often overlook, a force both silent and powerful, which physics calls mass? Mass is not just a number on a scale. It is a property of matter that shapes how we exist in space. It is present in every step, every hand lift, even in the way you hover between sleep and wakefulness. Mass is a measure of inertia, the ability to resist any change in motion. Imagine pushing an empty shopping cart. It moves easily. But if you load it with cartons of milk, bags of rice, and a few watermelons, the cart becomes stubborn, hard to move. No change in the environment, no special friction, and just the larger mass of the object requiring more force to move. This is inertia, a property that mass gives every object, quietly protecting its current state. Inertia does not only exist in objects, but is also directly reflected in our bodies. When you lift a grocery bag, the feeling of heaviness is not simply the weight exerted by Earth. In fact, the bag's mass measures how much your body must resist the change in the object's state. Your muscles respond, your ligaments and bones coordinate, and your brain adjusts the force needed to maintain balance. Mass, therefore, is a silent ally, but also a strict teacher, instructing us about force, motion, and our own limits. A magical aspect of mass is its invariance. Whether you are standing on Earth, jumping on the moon, or floating in the microgravity environment of the International Space Station, your mass remains intact. You do not become lighter or heavier. Only weight, the force of gravity acting on you, changes. This is why astronauts can float freely. Yet, when they want to move, they must still account for their body mass to control momentum and maintain direction. Mass is a silent presence, unaffected by gravity or environment, but always a key factor for motion to occur. Look around at every daily action to feel how mass governs your experience. When you walk, each step is a delicate negotiation between body mass and the ground. Your feet press down, your center of gravity shifts, your body adapts to maintain balance. Toddlers stumble not because they are weak, but because they haven't learned to balance body mass with the reactive force from the ground. Older adults with reduced muscle mass must step more carefully. The mass within our bodies is a partner in every movement, reminding us that stability results from continuous interaction between force and matter. In industrial and engineering environments, mass also plays a decisive role. When engineers design spacecraft, they must carefully calculate the mass of each component because mass directly affects momentum, the force needed to accelerate, and fuel consumption. An astronaut may float in microgravity, but body mass still determines how they move. A slight push creates prolonged motion, forcing them to learn how to control each part of their body to avoid collisions with ceilings, walls, or colleagues in space. Mass, in this case, is not just physics, it is gentle guidance on how matter operates. Next, consider gravity, the inseparable companion of mass. When you lift an object, you are not only resisting its inertia, but also the Earth's pull on it. The force you must exert equals the object's weight, mass multiplied by gravitational acceleration. A brick and a feather of the same mass? Not quite, but both are subject to their own inertia and gravity. In a vacuum, they fall at the same speed, but on Earth's surface, differing weight makes you feel the difference. This helps us understand more deeply the relationship between mass, inertia, and force in every action. Mass also creates momentum, a wonderful concept to see how mass and velocity interact. Momentum equals mass times velocity. A slowly rolling bowling ball can have a greater impact than a fast moving ping pong ball. When you stand in the path of a heavy object, you feel the hidden power of inertia, a vivid demonstration that mass is not an abstract number, but a real force in existence. And then when you observe the universe, mass becomes even more magical. Atoms are mostly empty space with a dense nucleus, yet it is this delicate arrangement that allows influence on the macroscopic world. An invisible particle, when combined with billions of others, can tilt a spaceship, knock over a cup of coffee, or generate the brute force of a truck. Mass, though silent, is the foundation for every physical interaction we experience. Mass is the silent backbone of reality, shaping every motion and force around us. From lifting a cup of tea, walking across a floor, to the macroscopic movements of planets, mass is consistently present, unchanging, independent of mood or circumstance. Understanding mass is learning to listen to the subtle forces shaping life, recognizing the harmony between physical principles and everyday experience. Imagine once again that you are standing in the living room, firmly holding a heavy chair. As you apply force to push it, you feel the resistance the object provides, as if it is saying to you, "Not so easy, try a greater force." This is inertial mass, the way an object resists changes in motion. You don't need to look at equations or read a textbook. You can feel this concept in every movement, from lifting a bag of rice, pulling a suitcase, to the final push of the refrigerator in the kitchen. Inertial mass is the silent partner in every everyday physical action, always present but rarely noticed. The wonder is that mass not only appears on a small scale, but also extends to the universe. Isaac Newton realized that the principles we experience when pushing an object on Earth also apply to massive celestial bodies. The simple yet profound law F equals m times a not only explains why a bicycle accelerates quickly, but also allows astronomers to calculate the orbits of planets. The greater the force applied to an object, the higher its acceleration. But that acceleration is always governed by mass. A bowling ball and a shuttlecock subjected to the same push will respond completely differently, visually illustrating the power and influence of mass in every motion. Newton also demonstrated that every action has an equal and opposite reaction. When you jump off a kayak, the boat moves backward slightly. When a rocket expels hot gas downward, it rises upward. This is the third law, a testament that every force is part of a cosmic dance where each force is balanced and mirrored. These laws are not just theoretical, they are the background music for all motion, from the daily rhythm of our bodies to the movement of planets and satellites in the universe. When it comes to gravity, mass exhibits another form, gravitational mass. Every object attracts every other object, and this attractive force is proportional to their mass, and their mass inversely proportional to the square of the distance between them. This means that the greater the mass, the stronger the gravitational force. Uh, the farther apart two objects are, the weaker the attraction. This is why the moon continues to orbit the Earth, and why an apple falls to the ground instead of flying upward. In a subtle way, the universe has unified inertial mass and gravitational mass perfectly, allowing Newton and later Einstein to build theories that accurately predict the motion of all objects, from tiny dust particles to massive planets. You can imagine gravitational and inertial mass as two sides of the same coin. When a bowling ball and a feather fall in a vacuum, both hit the ground at the same time. The Earth's pull acts according to gravitational mass, while inertial mass governs how they respond to acceleration. This unity, although seemingly obvious, is one of the strangest and most spectacular aspects of physics, and it paved the way for Einstein's theory of general relativity. Returning to everyday experience, you feel inertial mass every time you start moving after sitting still for a while. Your muscles stretch, your joints crack slightly, and it feels as though you are persuading your body to move. This is how inertia manifests in daily life, and you do not need physics knowledge to recognize this silent power. Once in motion, momentum takes over. The object continues to drift by inertia until an opposing force or friction causes it to stop. But the special thing is that inertial mass does not favor material or shape. A bag of feathers and a bag of sand, if they have the same mass, will react similarly when set in motion. The interior of the objects may differ, but the resistance to changing motion the essence of inertia is the same. This demonstrates the subtlety and elegance of mass. It does not judge, does not favor, it simply exists consistently. In scientific experiments, measuring inertial mass is relatively simple. A spring applies a fixed force to different objects, and the acceleration each object attains allows for mass calculation. An object with smaller acceleration certainly has a larger mass. This is why scientists have been able to compare objects for centuries without using traditional scales. In the laboratory, an inertial balance works like an oscillation measurement system. The heavier the object, the longer the oscillation period. A simple but effective method emphasizing the connection between force, motion, and mass in reality. The combination of inertial mass, gravitational mass, force, and momentum forms the foundation of classical mechanics. It allows humans to build bridges, design machinery, navigate spacecraft, and even measure celestial motion. At the same time, mass is also an everyday experience. It is the chair you push, the bag you lift, and the feeling of laziness when your body does not want to rise. In each small detail, mass is present, silent but undeniable, reminding us that all force and motion are based on a solid principle, verified over centuries. Mass, whether in Newton's laws or in daily experience, is the bridge between theory and reality. It gives us a visual perspective and a bodily sense of the universe, from throwing a ball, lifting a suitcase, to how planets move in their orbits. Every daily experience is a testament to the silent but persistent power of mass, a grand measure, both simple and profound, both scientific and poetic. If inertia is the character of an object, then gravity is the continuous dialogue the universe has with everything. You can feel it in everyday life without a scale or special measuring device. When you stand still on the floor, your feet press against the ground while simultaneously the earth gently pulls you toward it. And at the same time, you also exert a force back on this enormous planet. You may not realize it, but this simple action is an expression of Newton's third law. Every action has an equal and opposite reaction. It is not just an act physical principle, it is the continuous conversation between mass, force, and space, existing from the tiniest speck of dust to the massive sun. What is remarkable about gravity is that it is not limited to what we can touch or stand on. It extends through space, affecting every object with mass, from dust particles floating in the wind to satellites orbiting a planet. When you drop a pencil onto the floor, you are witnessing the same force that has kept the moon in its orbit for billions of years. This consistency and stability make the universe reliable. It is a silent but continuous rhythm, reminding us that all motion is guided by consistent principles, without exception. And if inertial mass is resistance to change, then gravitational mass is attraction, connection. Every object, large or small, pulls other objects toward itself. Gravitational force is impartial. It does not choose between a stone, a chair, a human, or a distant planet. This feature makes it an important tool for measuring mass without direct contact. By observing how objects interact, move, and accelerate, humans can estimate mass from a tiny marble in a laboratory to Earth, the Moon, or even massive galaxies. A classic example of this subtlety is Henry Cavendish's experiment in the late 18th century. Using a simple but extremely sensitive device, Cavendish measured the gravitational force between lead spheres and thereby inferred the mass of the Earth. Imagine being in a small wooden room, quietly observing small spheres oscillate, measuring the extremely subtle changes in the twisting angle of the suspension wire. The numbers obtained are not just data. They are proof that even a tiny force, when measured precisely, can open the door to understanding the entire planet. And from there, these principles have been extended over hundreds of years, enabling the discovery of masses that the naked eye can never see. In the universe, gravity also serves as evidence for the presence of invisible masses, dark matter. When observing stars orbiting the galactic center, astronomers notice that their speeds do not decrease as predicted by the observable mass. This indicates the presence of a gravitational force from an invisible mass, governing everything, yet emitting no light, reflecting nothing, and being impossible to observe directly. Gravity reveals the presence of these objects without them appearing before our eyes, like a detective noticing traces that others miss. Gravity is also the reason for the existence of tides. The moon pulls the oceans, creating bulges in its direction, while Earth also pulls back, forming a two-way interactive relationship. This is a beautiful example of the democracy of gravitational force. Every object is affected. Every object participates in this dance. We feel this rhythm when the sea rises and falls, when boats glide over the waves, and generations of sailors, poets, and ferrymen have connected with this rhythm for centuries. Even in the case of extreme masses like black holes, gravity remains honest and cannot be deceived. We do not see black holes directly, but observing stars orbiting the void allows us to infer the hidden massive object. This is how gravity becomes the scale of the universe. It does not care whether the object is visible or not. As long as mass exists, the force will reflect it. Light bending around galaxy clusters or stars is an invisible fingerprint reminding us that gravity is always faithful and consistent. In everyday experience, we also live with these principles, from maintaining balance while climbing stairs, lifting a heavy table, to feeling pulled sideways when a car takes a sharp turn. Each action is a testament to the silent perseverance of inertial mass and gravitational force. Inertial mass makes you resist change, keeping everything stable, while gravitational force connects all objects, creating structure and rhythm in the universe. Even modern technology applies this principle. Inertial navigation systems on spacecraft, accelerometers, and phones all rely on how mass resists acceleration to locate and measure movement. This simple yet powerful principle demonstrates that mass is not just a number, but a bridge between theory and reality, between everyday experiences and great discoveries in the universe. In short, from the inertia of the chair in the living room, the pull of the moon, to the mysterious presence of dark matter and black holes, mass is the heartbeat of the universe. It is both tangible and abstract, both familiar and grand. It is the reason motion can be predicted, forces can be measured, and the universe operates in delicate order. Mass is proof that every object, small or enormous, participates in the same grand exchange of force, motion, and time, opening the door to understanding, exploration, and appreciation of the hidden beauty of all things. Mass, when viewed through Einstein's lens, is no longer a dry number on a scale or a physical property separated from energy. It is a reservoir of potential, energy compacted, a seed for all activity in the universe. Even a small stone lying still on the floor carries within it the power to light up an entire city if one knows how to release the hidden energy inside. Every atom, every proton or neutron is a treasure of energy, quietly drifting in a state of rest, waiting for the opportunity to manifest itself as light, heat, or motion. When you bend down to pick up that stone, you are touching an enormous amount of energy, an entity invisible to the human eye, yet you can sense its presence through the weight and inertia of the object. Mass does not exist in isolation. It communicates silently, continuously across space, forming a vast gravitational network connecting all objects. The Earth revolves around the Sun, the Moon pulls the oceans, and Jupiter quietly adjusts the orbits of smaller planets around it. From such macroscopic movements to the tiniest oscillations within atomic particles, everything is influenced by mass and gravity. This network is so subtle that it is difficult to notice in daily life, yet it always exists, quietly maintaining order in the universe. When you walk, your arms swing in rhythm, or when you lift a heavy object, it is your mass, combined with gravity, that creates a silent dialogue with the Earth. On a larger scale, mass is the reason the universe has structure. Without it, stars, planets, and galaxies would be nothing but chaotic clouds of matter drifting aimlessly. But thanks to mass, energy is contained, creating pressure and inertia to form atomic nuclei, which in turn generate elements from hydrogen and helium to gold and uranium. These elements build planets, living beings, and ultimately ourselves. Every heartbeat, every step, even every breath, relies on the interaction of the mass of your molecules and cells with each other, with gravitational force, and with the latent energy within. Einstein expanded the vision of mass through the famous equation E equals mc squared per slide, transforming mass into a map of the universe's latent energy. Even when everything around you seems still, inside, trillions of atoms are bustling. That energy does not disappear. It exists within every atom, every electron, and every photon. When mass converts into energy in nuclear reactions, as in the sun or in a reactor, We witness directly the beautiful interaction of two entities seemingly distinct but actually one. The sunlight you feel on your skin, the warmth in your house, and the electrical energy generated from nuclear reactions are all vivid evidence of the unity between mass and energy. Even fundamental particles, when collided in particle accelerators, create entirely new particles, demonstrating that energy is not lost but transformed into mass. From a pure burst of energy, material particles are born with weight, charge, and unique character. This is not just theory, it is reality that we can observe and measure. Mass, in this profound sense, is energy that has taken its place, committed to exist and influence its surroundings. Upon closer observation, you realize that mass is not merely the weight of an object, but also a record of the universe's energy history. When protons and neutrons bind in a nucleus, the total actual mass is less than the sum of the individual particles' masses. This difference, called mass defect, releases energy to keep the particles bound together. Every atom is a vivid example of how energy and mass intertwine, maintaining stability for matter while allowing that energy to burst forth under suitable conditions. Not only in atoms, but in macroscopic structures like black holes, mass and energy exhibit this relationship in an extreme manner. When matter falls into a black hole, part of its mass converts into radiation energy, part contributes to the enormous gravitational force, sustaining the black hole's infinite hunger. Um, Mass and energy in this case dance in a violent yet strictly governed rhythm, showing that every object in the universe, big or small, is part of the same energy, mass, gravity, space-time system. Even in everyday life, you interact directly with this subtle transformation. When lifting a hot cup of coffee, stirring milk into tea, or walking on the sidewalk, you are interacting with the energy contained in the atoms of the cup, the liquid, and your own body. Mass seems rigid and inert, yet it is actually latent energy quietly participating in the universe's dance. Every time you feel weight, you also feel energy, cohesion, and the stability that mass provides. Even light, seemingly massless, bends when passing near massive objects because it carries energy. This demonstrates that gravity acts not only on mass, but also on energy, unifying two seemingly different entities into one. Space-time curves, orbits adjust, and the universe operates according to the subtle rhythm of energy and mass. Everything is connected: mass, energy, gravity, and time. Every atom, every particle, every planet, every star is part of a continuous network where energy can transform into mass and mass can release energy. The seemingly still world around you is in fact filled with latent energy, and mass is the means by which this energy manifests steadily, measurably, and interactively. Every time you lift a stone, stir tea, or gaze at the sky, you are touching a part of the universe where energy and mass communicate in silence, persistently, and with absolute fidelity. Mass, when observed at ordinary speeds, seems like an invariant property, a solid number attached to an object. A stone weighing 1 kilogram still weighs 1 kilogram, whether you place it on a table or hold it in your hand. But as we approach the speed of light, the universe suddenly becomes strange. Mass is no longer something easily grasped, it merges with energy, and all old definitions of heavy or light begin to waver. In special relativity, Albert Einstein opened a new perspective. What truly increases as an object moves rapidly is not its rest mass, but its total energy, or more precisely, the inertia the object exhibits. Rest mass, or invariant mass, remains steadfast. It is the number assigned to a proton, neutron, or atom on its birth certificate. Whether you move as fast as a rocket or stand still on Earth, rest mass does not change. But when energy is pumped into the system, when an object approaches the speed of light, the total energy increases, making it harder to change the object's velocity. That is why physicists used to speak of relativistic mass. But today we understand that this increase is an expression of energy, not of actual rest mass. Imagine you are piloting a spacecraft into space. When accelerating from a few hundred kilometers per hour to a few thousand kilometers per hour, you hardly notice any change in inertia. But when speed approaches hundreds of millions of meters per second, every bit of energy you add no longer increases velocity, but manifests as a heaviness of inertia. The object seems to resist you, not because its weight has changed, but because the energy in the system has increased to the point that inertia is more pronounced. This is why, in theory, no object with rest mass can reach the speed of light. To do so would require infinite energy, which is impossible to achieve. This concept is not limited to imagining a spaceship. It reflects directly in smaller scale experiences within atoms and fundamental particles. When protons collide in particle accelerators, energy transforms into mass, creating entirely new particles that never existed before. You can imagine this scene like a ballroom where particles dance. Energy spins and combines to generate a new entity. Mass, in this case, is the result of compressed energy, energy that has chosen to remain stationary in space rather than continue moving. The deeper we go, the more unified the relationship between energy and mass becomes. Not only is light bent by gravity, but even electromagnetic energy and the motion of particles within an atom contribute to an object's mass. An atom is heavy not just because of protons and neutrons, but also due to the binding energy holding them together, due to the gluons connecting quarks in protons and neutrons, due to the continuous oscillations and movements of fundamental particles. Each atomic mass is a living synthesis of energy, motion, and fundamental forces, from the strong force stabilizing the nucleus to the electromagnetic force shaping the electrons around it. Imagine a uranium nucleus. It contains 92 protons and 146 neutrons, an enormous total mass, yet the actual nuclear mass is less than the sum of the separate particles. The missing part is binding energy, the energy sacrificed to keep the particles tightly bound. When a uranium nucleus undergoes fission, the binding energy is released, converting mass into energy in the form of heat, light, and radiation. This is the essence of nuclear reactions, the reason why the sun shines and nuclear power plants operate. The initial rest mass transforms but does not disappear. It becomes energy, participating in the universe's vibrant rhythm. In everyday life, mass and energy also intermingle, though their manifestation is subtler. When you drink a hot cup of coffee, the thermal energy slightly increases the mass of the cup and liquid, although the change is extremely small. When two atoms bond to form a molecule, a small amount of energy is released, meaning the final mass of the molecule decreases slightly. Chemistry, in this way, is a subtle game of energy and mass where every interaction leaves an imprint on the overall mass. Mass, therefore, is not a static number, but a living picture of how energy flows through every object. It reflects motion, bonding, and latent energy. When you hold a stone, look at the sky, or walk on Earth, you are touching a part of the energy universe, a portion of energy that has chosen to exist in the form of mass, silently contributing to gravity, inertia, and the rhythm of the cosmos. Mass is the embodiment of energy, the silent accounting ledger of the universe, recording what is bound, what is moving, and what remains potential to be released. With this perspective, everything around you, from the tiniest atom to the most distant stars, has a story to tell, a story of energy, motion, and connection, of mass and time. Rest mass, relativistic mass, binding energy, and the oscillations of fundamental particles all are rhythms in the complete dance of the universe. Mass is no longer a dry number, but a window into the profound nature of matter, energy, and ourselves, beings living in a universe brimming with potential. Exploration of the Higgs field and the Higgs boson opens one of the deepest mysteries of the universe: why all matter exists with mass, and why atoms do not simply drift freely at the speed of light like photons. Imagine the empty space you usually think of as a simple void. In reality, it is a dense fabric of energy, a vibrant spacetime with invisible fields permeating everywhere. Each particle of matter, as it moves through this field, must interact with it, and it is this interaction that gives rise to the mass we perceive. Without the Higgs field, these particles would be like beams of light, unable to form atoms, molecules, or stable matter. The universe would be empty and motionless in ways we can hardly imagine. Imagine walking through a room filled with cosmic molasses. Some particles move through it easily, almost unimpeded, like photons gliding through space with no rest mass. Other particles get stuck, having to drag themselves step by step, like a celebrity at a crowded party with people pressing around them. Each interaction with this molasses makes the particle experience a resistance, and this resistance is precisely the mass the particle carries. Mass, in this way, is no longer an intrinsic property, but the result of an energy relationship, a subtle conversation between the particle and the Higgs field that envelops the universe. From this idea arises one of the greatest questions. How can we prove the existence of such an invisible field? The answer lies in the Higgs boson, the fundamental particle that manifests the Higgs field, analogous to how the photon embodies the electromagnetic field. But discovering the Higgs boson is far from simple. It is an extremely heavy particle, unstable, and it disappears almost immediately. This requires physicists to create collisions at extremely high energies, energies that nature rarely provides since the Big Bang. And this is where the Large Hadron Collider, LHC, comes in as a marvelous machine. A gigantic circle over 25 kilometers long lies deep beneath the border of France and Switzerland, where protons are accelerated to near the speed of light and made to collide. Each collision is an extreme explosion of energy, creating conditions never seen since the early universe. When this energy concentrates sufficiently, a Higgs boson can appear for a brief moment before decaying into other particles, leaving traces that the sophisticated detectors at the LHC can observe. The success in observing the Higgs boson in 2012 was not only evidence for the existence of the Higgs field, but also completed the Standard Model, the theoretical framework describing all fundamental particles and their interactions except gravity. This was a historic step. For the first time, humanity demonstrated that mass is not a static property, but the result of energy and interaction. It not only explains why you and your cup of tea have mass, but also why every atomic structure in the universe is stable and able to form matter. This leads us to a deeper understanding of the nature of matter. When we look at any object, from a grain of sand to a planet, from a photon to a human, we are observing complex energy relationships. The rest mass of each particle is a form of static energy, but it is the interaction with the Higgs field and other fields that produces their full physical behavior. It explains why protons and neutrons remain stable within nuclei, why electrons orbit nuclei without falling in, and why atoms can combine to form molecules. Another, more philosophical perspective is to recognize that the universe is never truly empty. The space we think of as void is filled with energy fields, where energy and matter continuously interact and transform. Every particle we observe is a product of this process, and mass is the way these interactions manifest externally as a subtle, stable, and persistent rhythm. Even when particles move near the speed of light, they retain their inherent nature. Only the motion of energy becomes more dominant, producing wondrous effects such as time dilation or spatial contraction. Importantly, these discoveries are not confined to laboratories or theory. They directly influence technology and daily life. Atomic clocks on GPS satellites must account for special relativity and the Higgs field to ensure precise positioning. Particle accelerators open doors to research on dark matter and dark energy, and fundamental physics models guide new technologies in medicine, materials, and energy. The universe is no longer a distant stage. It is an interconnected system where energy and mass dance in every moment. Mass, therefore, is not a dry number. It is the heartbeat of the universe, a stable anchor in a sea of fluctuating energy. It is the result of interactions, the product of fundamental forces and invisible fields, from the strong force to the Higgs force, from nuclear binding energy to motion near light speed. It allows atoms to form, matter to exist, and us to observe the world. Above all, it reminds us that even the seemingly most rigid things, a kilogram, a proton, an electron, carry within them a story of energy, interaction, and the delicate stability of the universe. Every time you touch an object, look up at the sky, or follow a beam of light, you are witnessing the result of profound interactions, written over billions of years of physical evolution. Mass is not merely material presence. It is evidence of the intimate connection between energy, the Higgs field, and space-time. It shows that from the smallest particle to the farthest stars, the universe operates like a complex symphony where mass is one of the most delicate notes, reminding us that all existence is the result of a magnificent and wondrous dance of energy. If the Higgs boson is the host of the particle party, then the neutrino is the quiet guest, almost invisible, yet holding the key to many of the universe's deepest mysteries. They move through the Earth billions of times per second, barely interacting with anything, passing through your body, through buildings, through oceans, and the depths of the Earth. Their presence seems like an illusion, Yet each neutrino carries a subtle message about the nature of matter and energy. When physicists discovered neutrino oscillations transforming from one flavor to another, they realized an important truth. Particles that seemed weightless actually have an extremely tiny mass, enough to alter the way they interact and exist in the universe. Neutrino oscillation is a vivid demonstration of a profound philosophical principle. The universe is always more complex than it appears. A particle's mass does not merely determine its weight. It is how nature shapes its behavior, interactions, and sphere of influence within the cosmic design. The photon, with zero mass, never stands still. It is not constrained by the Higgs field and can freely traverse infinite space, carrying light, heat, and information from distant stars to the observer's eyes. The masslessness of the photon explains why light from faraway galaxies can travel billions of years before reaching Earth, a journey long yet continuous and undiminished. Meanwhile, the W and Z bosons, with masses tens of times that of a proton, move much more slowly and exist only fleetingly. They mediate the weak nuclear force, determining how particles decay and interact. Their large mass is why the weak force has an extremely short range, limited to distances smaller than an atom. It is the interaction of these bosons with the Higgs field that determines the scope and influence of the weak force, allowing processes like radioactive decay to occur stably, shaping life and matter in the universe. Small particles like electrons also rely on the Higgs field to gain mass, allowing them to orbit the nucleus without being pulled straight in. The electron's mass determines its orbit and energy levels, which in turn shapes the chemistry of the universe, the atomic bonds, molecules, chemical reactions, and ultimately life itself. Without electron mass, atoms could not exist stably. Chemistry would fail, planets, oceans, and life would not form. Mass, therefore, is not merely a physical parameter, but a prerequisite for an organized and observable universe. Neutrinos, though tiny and almost non-interacting, reveal other secrets. They allow physicists to test theories of dark matter and dark energy, the mysterious components that make up most of the universe's energy, yet remain poorly understood. These fleeting, elusive particles open paths for future research, reminding us that the Standard Model, though perfect in describing most fundamental particles and forces, does not tell the whole story. The story of the neutrino reminds us that the universe always contains deeper layers, where energy, mass, and interactions lie hidden, waiting for humans to explore. The mass of each particle, or the lack thereof, tells a story about its role and influence. Photons, always moving, spread endless light. W and Z bosons, heavy, appear only briefly yet shape critical physical processes. Electrons with just enough mass create atoms and chemistry. Neutrinos, small and silent, carry messages about unresolved mysteries. Each particle is a note in the cosmic symphony, and mass is how rhythm, pitch, and intensity are expressed. Imagine a subatomic dance. Particles do not stand still. They move, interact, collide, and oscillate through space and time. Mass is the subtle resistance that particles feel when moving through invisible fields like the Higgs field, determining their speed, mobility, and influence on the surrounding environment. Without mass, a particle would be completely free. With too much mass, it would be bound and slow. This balance is the foundation for all structures, from atoms to galaxies. In the grand picture, we begin to realize that mass is not a fixed or simple value. It is the result of the relationship between a particle and the surrounding energy. The mass of W and Z bosons makes the weak force local, the mass of the electrons stabilizes atoms, and the tiny mass of neutrinos allows flavor oscillations, opening new avenues for observation. All of this creates a perfectly designed universe, where every particle, every force, and every form of energy plays an irreplaceable role. Mass, whether heavy or light, static or dynamic, is the language the universe uses to tell its story. From the light of distant stars, to neutrinos gliding through you unnoticed, to W and Z bosons appearing in a fleeting instant, everything speaks of a universe woven from energy, interactions, and intricate structure. And every time scientists create, observe, or interpret these particles, they are not merely discovering physics, they are listening to the story of the universe itself, a story of mass, energy, and existence. When looking up at the night sky, each point of light is not just a star, but also a mirror reflecting how mass operates in the universe. Even the most distant galaxies are not still. They rotate, interact, and attract each other, tracing invisible curves in space. We cannot step on a scale to measure the mass of a galaxy, nor can we lift it or hold it in our hands. Instead, we observe how it influences its surroundings, from the motion of stars in orbit to the way light bends as it passes through galactic clusters. All these effects are indirect yet clear evidence of the mass they carry. Mass on the macroscopic scale is both cause and consequence. It generates gravitational force, yet at the same time, gravity reveals mass. Each galaxy is a highlight on the cosmic map, where matter and energy accumulate in a balanced and intertwined manner. But upon closer observation, we realize that most of the mass does not come from the bright, sparkling stars we see. A large portion of the universe's mass belongs to dark matter, a nearly invisible substance that emits no light and no electromagnetic radiation. We do not know what dark matter is, but we know it exists through the effects it produces. Stars orbit galaxies faster than expected, light bends unusually, and galaxy clusters are drawn toward each other. Dark matter is a profound testament to the separation between matter and mass. It can possess mass, yet we cannot see or touch it. In everyday language, we might be tempted to think that matter and mass always go hand in hand, but the universe reveals a subtler truth. Mass can exist as energy, as an interaction force, and even as something we have yet to categorize. It is a reminder that human understanding of matter is only a fraction of the larger picture. Another example illustrating this subtle connection is how light interacts with gravity. Photons, though massless, are still bent when passing near massive objects. Einstein described this by saying that spacetime is curved by mass, and photons simply follow that curve. In this case, mass is not a physical object you can hold, property that bends the landscape of the universe, shaping the paths that other particles, both massive and massless, must follow. Imagine a river of light flowing through a region of galaxies. These photons have no rest mass, yet they carry momentum and therefore respond to curved spacetime. They glide along the curves created by mass, like leaves drifting along a winding stream around large rocks. Mass in this case is invisible, yet its influence is undeniable. This demonstrates that mass does not merely determine weight or inertia, it is the way the universe instructs particles on how to move, interact, and form structure. On a smaller scale, even within galaxies, mass and matter dance in a complex choreography. Stars form from clouds of gas and dust where gravity pulls particles together. This process generates heat and pressure, leading to nuclear fusion reactions that ultimately produce light and energy. The mass of the particles in a star shapes reaction rates, internal pressure, and how the star maintains stability. If electrons or protons did not have the proper mass, atoms would not exist stably, stars would not burn correctly, and energy cycles in the universe would be completely altered. Mass also governs the interactions between galaxies and galaxy clusters. Gravitational fields create orbits, collisions, and mergers, giving rise to large-scale structures such as superclusters and the cosmic web. Matter and mass together create the landscape we observe, a colossal lattice where particles, stars, and galaxies orbit invisible centers of gravity, maintaining a delicate balance between motion and force. The wonder lies in how every aspect of the universe, from the tiniest particle like the neutrino to the largest galaxy clusters, follows the same principles. Mass is the universal language the cosmos uses to tell its story. It determines how particles interact, how forces propagate, and how matter arranges into structure. Because of this, we can observe galaxies, admire the light from distant stars, and detect the traces of dark matter, all thanks to a subtle, nearly invisible property with immense influence: mass. And when we observe galaxies, we do not just see scattered points of light in the universe, but also sense the presence of a subtle, silent, yet universal force. That force is gravity, the macroscopic manifestation of mass, pulling galaxies together, shaping their motion, and creating the overall structure. Every time light bends around a galaxy cluster, every time a star falls into orbit, we witness a grand dance between matter, mass, and spacetime. Mass is not just a number in an equation. It is a catalyst for interaction, a guide for motion, a witness to cosmic structure. And even when we do not fully understand all the forms of matter and energy that exist, mass remains at the core, a property invisible yet profoundly influential, connecting scales from subatomic particles to galaxies, from gravity to light, from neutrinos to photons. Understanding mass is the beginning of understanding the story of the entire universe, a complex symphony of matter, energy, and forces, where everything is connected, influencing one another, and existing thanks to this subtle property. Dark matter is not just an abstract concept, it is a silent force operating the universe, something invisible yet decisive in the fate of galaxies. When astronomers observe galaxy clusters, they find that galaxies move at speeds that the gravity from visible matter cannot explain. They are not torn apart, nor do they collapse. Instead, they follow a stable rhythm, as if an invisible hand is holding everything together. In fact, that hand is dark matter, a mass that does not emit light, does not interact electromagnetically, but exerts a powerful influence through gravity. One of the most compelling pieces of evidence comes from gravitational lensing. When light from galaxies or quasars passes near a massive object, its path is bent. These distortions, no matter how small, reveal the mass density that the light has traversed. In many cases, the resulting images are stunning. Perfect Einstein rings, delicate arcs curving around a central galaxy, or galaxy duplication, where a single galaxy appears twice in the sky due to bent light. Each curve is an invisible map, tracing the distribution of matter, both visible and invisible. A famous example is the Bullet cluster, where two galaxy clusters collided. The hot gas, visible matter that makes up most of the clusters, slowed down, spread out, and created bright streaks in X-rays. But when scientists measured gravitational lensing, most of the mass did not coincide with the gas. It passed straight through the collision. Most of the gravitational pull comes from something that does not collide, does not interact, and does not shine: dark matter. This is the clearest evidence that dark matter is an independent entity, exerting a strong gravitational effect while remaining nearly invisible. Dark matter not only keeps galaxy clusters bound, it also forms the large-scale structure of the universe. As the early universe cooled, dark matter arranged itself into vast filaments and dense nodes, creating a cosmic web. Galaxies formed along these filaments, like pearls strung on an invisible thread. The vast voids between filaments demonstrate the uneven distribution of mass, where dark matter determines the shape of the universe we observe today. This invisible mass accounts for up to 85% of the total mass in the universe, far exceeding the mass of stars, planets, and gas. While visible matter is easier to observe, it is dark matter that serves as the pillar for the entire structure. Without it, galaxies might never have formed, or they would have disintegrated, losing stable orbits and failing to create star systems, planets, or any form of life we know. Dark matter is the invisible skeleton of the universe, keeping everything from drifting into nothingness. The story of dark matter also opens another horizon. It shows that the universe is not always as it appears to the naked eye. Half of the story may lie beyond visual reach, yet it can be felt through gravity, through motion, through bent light. This challenges human intuition. We are accustomed to evaluating objects by shape and color, but on a cosmic scale, the most important things are invisible. We must learn to weigh the universe using sophisticated tools, mathematics, theory, and patient observation. Astronomers also use the cosmic microwave background, the afterglow of the Big Bang, as a primordial map. The fluctuations in this background contain information about the density of matter and energy in the early universe. Analyzing these fluctuations allows scientists to estimate the total mass, including the invisible component. Results from multiple methods, stellar orbits, gravitational lensing, background radiation, converge on a consistent picture. Most of the universe's mass is dark matter, silent, yet governing everything. Dark matter also challenges the limits of our understanding of physics. It does not interact electromagnetically, does not shine, does not collide, yet it curves space-time, slows light, and shapes orbits. This invisible mass teaches us that in the universe, the most important influences are not always intuitive. It reminds us that reality is far larger than what the eyes can see, and science is the only tool to explore what lies hidden behind the cosmic night. Dark matter also raises philosophical questions. If most of the universe is invisible, how should we regard the role of humans and visible matter? We are observers, striving to understand a universe where most of the weight and structure is concealed. The mass we cannot see is what binds everything together, and thanks to it, the universe remains stable and capable of producing life. When observing galaxy clusters, we realize that dark matter is the invisible web keeping everything in place. This unseen mass exceeds all that we can see, and it determines the fate of galaxies, galaxy clusters, and the large scale cosmic network. Thanks to dark matter, galaxies do not drift into nothingness, stars maintain their orbits, and the entire structure of the universe remains orderly. The universe, ultimately, is a picture of a delicate balance between the visible and the invisible, between light and darkness, between tangible matter and intangible mass. Dark matter is evidence of this subtlety, showing that in all the grandest things, real power does not necessarily manifest visibly. It exists silently and patiently, shaping and sustaining the order of the cosmos. That invisible mass, in its quietude, is the foundation for all that shines brightly in the night sky. Dark matter, in its profound mystery, continues to challenge human intuition and observation. It does not emit light, does not collide, does not produce sound or radiation, yet it shapes the entire fate of the universe. When scientists look at stellar orbits, at galaxy clusters, or at the subtle distortions of light through gravitational lensing, they see a unified reality. Most of the mass in the universe does not reside in objects visible to the naked eye. Dark matter exists, and it accounts for about 85% of the total mass of the universe. Unknown particles, hidden energy fields, or novel physical forces all are silently pulling galaxies, keeping them from disintegrating, and creating the invisible framework on which all visible matter depends. The search for dark matter takes us to laboratories deep underground where experiments are shielded from cosmic rays and background noise, waiting for a tiny ping from rare dark matter particles interacting with ordinary matter. Although no direct results have been obtained so far, this silence does not dampen scientists' enthusiasm. They know that dark matter is not a numerical error or a miscalculation. It is a real component, a crucial agent shaping the universe. Each failed experiment merely reminds us that the universe still holds secrets beyond human reach, that silence does not mean non-existence. The idea that most of the universe's mass is hidden and invisible leads us into an even deeper realm of physics, the quantum world. Here, the concepts of matter, energy, and mass become subtler and more magical than any visual representation. Space is not empty. It is a sea of energy fields, full of constant oscillations and continuous change. Every particle in the universe, from electrons and photons to hypothetical dark matter particles, is a ripple in its corresponding field. When we observe a particle, we are actually witnessing a local oscillation of a field extending throughout space. And it is through the interactions of these fields that mass arises, not as a label attached to a particle, but as the result of a delicate network of interactions. One of the strangest contributors to mass is the quantum vacuum. Imagine a seemingly empty space, yet one seething with continuous oscillations. Even when no matter is present, quantum fields still vibrate, creating virtual particles, transient entities that appear and vanish so quickly they cannot be observed directly. These virtual particles, though existing only for a fleeting moment, profoundly influence real particles, contributing to their mass through continuous, invisible yet real interactions. A metaphor helps illustrate this concept: a boat on a lake. The lake is the quantum field, the boat is the particle. The surface may appear calm, but underneath are subtle ripples. As the boat moves, it interacts with these ripples, and it is these invisible interactions that create resistance, producing the perceived mass of the boat. In the quantum universe, particles do not possess intrinsic mass. Mass is the consequence of the complex interplay between fields, oscillations, and invisible forces around them. It has also been discovered that in protons and neutrons, most of the mass does not come from the quarks inside. Quarks are actually very light, but the powerful energy of the strong nuclear force holding them together contributes the majority of the protons and neutrons' mass. It is a strange paradox. The energy that keeps everything bound becomes mass. Like building a house from ultralight materials but using so many structural connections to hold it together, the weight of the entire structure is concentrated in the bonds that keep it intact. Dark matter, in a sense, operates according to similar principles but on a cosmic scale. It is the invisible network maintaining order among galaxies, galaxy clusters, and cosmic filaments. Physicists speculate that dark matter may consist of extremely rare particles, WIMPs, axions, or sterile neutrinos, entities that interact almost not at all with light but have mass and interact through gravity. They are the whispers of the universe, silently affecting everything, yet almost impossible to detect directly. It is precisely this silence and elusiveness that makes dark matter poetic. It teaches us that in the universe, influence does not always accompany direct observability. Most of the universe, in terms of mass and energy, remains hidden from view. Yet, through gravity, gravitational lensing, and other subtle observations, we can still sense its presence, like seeing the shadow of a person in dim light. And when we combine dark matter with dark energy, the phenomenon accelerating the universe's expansion, the overall picture becomes overwhelming. 95% of the universe is invisible, silent, and elusive. Only the remaining 5% comprises everything we have touched, seen, or are familiar with. Understanding and measuring the invisible is not merely a scientific achievement, it is a philosophical journey, a reminder that the universe is vaster, more wondrous, and subtler than any visual representation we could ever imagine. In the silence and mystery of dark matter, we learn that the greatest forces need not be loud or obvious. It exists, shapes everything, and challenges us to reconsider the notions of mass, matter, and reality. Ultimately, the universe is a symphony where particles, fields, and invisible forces collaborate to create a wondrous order, where mass is not just matter but the result of an ongoing, continuous quantum dance. In the vast canvas of the universe, where galaxies race across the endless backdrop of space, vacuum energy is not a mere detail. It is a subtle yet decisive component, an underlying rhythm that governs the entire cosmos. When we look deep into the seemingly lifeless voids between stars, we see that these spaces are filled with oscillations, delicate vibrations, silent ripples of quantum fields. Space is no longer empty. It is an ocean of continuously flowing energy, a dynamic tableau of matter and unknown forces, where every particle and every interaction leaves its imprint on the structure of the universe. This vacuum energy is a type of energy not directly tied to visible matter. It exists even when all atoms, all photons are removed, and the system is cooled near absolute zero. These underlying oscillations, though tiny and almost imperceptible, produce measurable effects, such as the Casimir effect, where two metal plates placed close together in a vacuum are drawn toward each other due to an imbalance in quantum fluctuations. This is clear evidence that emptiness is not truly empty. It has energy, and according to Einstein's equation, this energy is equivalent to mass. It curves, influences, and shapes the way gravity operates. The idea that space itself carries energy, thereby contributing to gravitational force, forms the basis for explaining the accelerated expansion of the universe. When astronomers discovered that galaxies are not only receding from each other but doing so at an increasing rate over time, they named this strange repulsive force dark energy. And dark energy is likely the cosmological manifestation of vacuum energy, an invisible, silent, yet extraordinary force, inflating the very space it inhabits. It is fascinating to realize that Einstein, when introducing the cosmological constant to keep the universe static, inadvertently predicted a phenomenon we would only discover decades later, that space itself could resist gravity and even drive expansion. Imagine this energy as an invisible net stretching across the universe. Each time space expands, each time galaxies move apart, this net stretches, generating an outward pressure, an invisible, steady, gentle force that cannot be stopped. Not a violent explosion, but a prolonged breath, soft yet persistent. The wonder is that energy requires no matter to exist. It persists in the emptiness we once thought was void, and from it produces measurable effects, contributing to the total mass and dynamics of the universe. While dark energy governs expansion, dark matter, with its strong yet almost invisible gravitational nature, holds galaxies and galaxy clusters together. The combination of these two forces, a quiet repulsion and a silent holding force, creates the strange yet perfect balance of the universe. It explains why galaxies exist, why the large-scale structure of the universe is not disrupted, and why all visible matter, from stars to planets, can assemble into stable systems. Dark matter and dark energy, though comprising up to 95% of the universe, silently shape everything we observe. To understand better, we return to the quantum world. The quantum vacuum is not just a repository of energy, but a place where particles are formed. The underlying oscillations in quantum fields generate virtual particles, fleeting ripples that appear and vanish, yet directly affect the mass of real particles. Like a stretched fabric, each vibration leaves subtle impressions, and these impressions are mass. A proton is not heavy because the quarks inside it are heavy, but because the energy of the strong nuclear force binding them together, energy converted into mass via E equal mc fuero. Mass, in this sense, is not a primordial attribute, but a consequence, an echo of invisible forces and surrounding energy fields. This imagery helps us envision the universe as a symphony. Dark energy, dark matter, quantum fields, particles, and oscillations all interacting, creating a delicate balance. Mass is not just matter, it is the harmony of forces, vibrations, and structure. It is a language, a whisper of the universe through which every particle, every galaxy, and even the entire cosmos communicates. Finally, the most wondrous realization is that everything we see, touch, or experience, from sunlight and planets to ourselves, is the result of interactions hidden deep within quantum fields and oscillations. Vacuum, dark matter, dark energy, and mass all are interconnected, transforming the invisible into influence, like turning nothingness into reality. When we enter the quantum world, we learn that the universe is not merely empty space for matter to occupy, but a complex, vibrant system where every oscillation, every ripple, and every particle contributes to the integrity of the structure. And this realization brings profound humility, while simultaneously inspiring awe. We live in a universe where most of it is silent, invisible, and beyond direct grasp. Yet even that silence and emptiness contain the power to create, sustain, and shape the entire reality. Mass, energy, and matter, ultimately, are the melodies of a quantum symphony, where the universe continually hums, and each oscillation, each ripple tells the story of the wondrous nature of everything around us. Mass, as we have come to realize, is not merely a number on a scale. It is a direct manifestation of energy, an echo of existence within the vast fabric of space-time that Einstein called curved space. When you place an object on a soft surface, the fabric dips under its weight. On a cosmic scale, planets, stars, and even tiny particles distort the flow of time and space. This brings a profound realization. Mass is not simply weight, but a presence capable of bending the entire reality around it. Every kilogram, every gram, every subatomic particle contributes to a delicate space-time dance, where everything interacts, curves, and responds continuously. This effect, most pronounced in extremely massive objects like neutron stars or black holes, is not just theoretical. When an observer looks from afar at the event horizon of a black hole, time appears to stop for objects near it. 1 second near a black hole may correspond to centuries in the rest of the universe. And this is not imagination. It is a mathematical reality, confirmed through models of gravitational interactions and light around black holes. Even without direct contact, we perceive the influence of mass on time. Everything, from atomic clocks on GPS satellites to distant galaxies, participates in this complex network. The story does not stop at time dilation. It extends to the concept that the very energy in empty space, vacuum energy, also plays a role in this picture. Quantum field theory predicts that this energy is vastly larger than what is observed, a discrepancy up to 10^4 times. This is one of the worst theoretical predictions in the history of physics. Yet this difference is the key that opens profound questions. Are there undiscovered cancellation mechanisms? Does our current mathematics miss a fundamental piece? Though full answers are lacking, the micro-effects of vacuum energy are observable, from the universe's expansion to subtle pressures in the voids between galaxies. The vacuum is no longer a passive backdrop. It is a dynamic actor, bending and shaping the universe like an invisible yet real force. Imagine the vast voids between galaxies as calm seas where invisible ripples of vacuum energy whisper. Mass, matter, energy, all interact with spacetime, producing subtle effects invisible to the naked eye. As we approach massive objects such as giant stars, these distortions become pronounced. Time slows, orbits curve, light bends. Even the concept of simultaneity becomes relative. Two events occurring at the same moment for one observer may not be simultaneous for another observer elsewhere, or within a stronger gravitational field. Every particle, planet, and galaxy contributes to a 3D map of time's flow, and mass is the subtle measure that shapes that map. In empty space, where vacuum energy dominates, small but continuous effects produce long lasting impact. The expansion of the universe, driven by dark energy, is a direct result of emptiness carrying energy and pressure. Galaxies move apart not because they are directly pushed, but because the space time fabric they inhabit is expanding. This invisible energy becomes the cause, and existing mass becomes the guide. It is a strange balance where the unseen and the visible coexist and operate together. Mass does not merely bend spacetime quietly, it directs the motion of every object. Earth's orbit around the sun, the moon's movement around Earth, even tides and ocean currents all follow the geometric rules inscribed on this stretchable fabric. Gravity, according to Einstein, is not a force in the traditional sense. It is the natural result of mass distorting spacetime. Every motion, every force, every effect we observe is a consequence of the wondrous interaction between energy and the universe's structure. Even familiar daily technologies like GPS systems rely on this understanding. Atomic clocks on satellites must be calibrated to compensate for time dilation due to gravity and motion. A discrepancy of a few microseconds per day can make us lose tens of kilometers. This demonstrates that mass and energy are not abstract concepts. They directly affect reality, shaping how we locate ourselves in space. Finally, mass, when examined deeply, becomes both a philosophical and physical puzzle. It arises from quantum fields, is the consequence of energy, bends spacetime, and simultaneously binds all objects to the flow of time. Mass alters moments, creates relativity in each being's experience, and deftly connects the visible with the invisible. Every particle, every star, every galaxy is a note in the symphony of spacetime, where energy, mass, and time intertwine, creating the complex yet exquisitely delicate reality we call the universe. In this journey of discovery, we learn that physics does more than explain phenomena. It opens a window into the deep nature of reality. Mass, energy, and time are no longer separate concepts. They are an interacting network, a hidden dance, a story about existence, about how nothingness becomes tangible, and about how the universe continuously expresses itself through invisible ripples of energy and mass that bend time. Mass, as we have just explored, is a profound phenomenon, seemingly both tangible and elusive, both an object of study and a narrative. It is inseparable from the universe, not only appearing in experiments or equations, but also creating the subtle rhythm of space-time. When we attempt to peer into its true nature, we realize that every particle, every field, every vibration of energy contributes to the experiences we call mass. Like a cosmic symphony, mass is the low note, the underlying pull, the anchor holding objects in the vast fabric of spacetime, while also being the source of the distortion we call gravity. While current theories, from the Standard Model to general relativity, provide tools to describe and predict the behavior of mass, many questions remain unanswered. Why do particles have different masses? Why is the electron thousands of times lighter than the proton? Why is the top quark heavier than a gold atom? Equations allow us to input these values, but they do not explain their origins. Mass, it seems, has an independent essence, existing both as a physical constant and as a manifestation of a larger system that we have yet to fully recognize. Dark matter, with its invisible presence yet clear gravitational influence, is evidence of even deeper layers of mystery. We cannot observe it directly, but we see how it bends the orbits of galaxies, how it contributes to the large-scale structure of the universe. Perhaps within dark matter lies the answer to mass, a particle yet undiscovered, a force yet unconsidered, or a form of energy not yet described in the Standard Model. It reminds us that the universe is a complex tapestry, where gaps and voids also act as notes, adjusting the rhythm of the whole. Mass is also tied to inertia, the resistance to any change in motion. We understand inertia through Newton, but its deeper origin remains a mystery. Some physicists propose that inertia may arise from interactions with vacuum energy, as if particles and surrounding fields are subtly negotiating speed and motion. If true, mass is not merely weight or gravitational force, but also a form of dialogue, a hidden message between physical entities, between spacetime and energy, a continuous process that produces the sensation of heaviness in the universe, On the microscopic scale, string theory offers another perspective on mass. Instead of discrete points, particles are vibrating strings, oscillating at different frequencies. The mass of a particle is the note that the string produces, a harmony of geometry, energy, and identity. Yet string theory remains a speculative hypothesis, a delicate picture whose outlines we have only begun to glimpse. It opens the prospect that mass is not an intrinsic property, but a manifestation of a deeper structure, a hidden rhythm among layers of energy, vibration, and spatial geometry. Similarly, loop quantum gravity attempts to quantize space-time, transforming space from a continuous surface into a network of quantum loops. In this model, mass and energy become properties of geometry, emerging from how loops connect and interact. Mass, therefore, is no longer a substance contained within matter, but the result of the deeper structure within the universe's quantum fabric. It is an emergent phenomenon, a behavior arising from the whole rather than a discrete element. Even in the philosophy of physics, mass carries subtle meaning. It does not merely orient space, but also sets the rhythm of time. Mass curves space-time, slows time, and shapes the flow of events. Each particle is an anchor, a stamp in the universe's temporal map. Time is not uniform. It is supple, elastic, bending according to the presence of mass and energy. Mass becomes a measure of depth, not only of objects, but of their influence in the cosmos. One could say that mass is the link between the tangible and the intangible, between matter and fields, between presence and behavior. It arises from subtle interactions, from vacuum energy, from microscopic vibrations, and at the same time manifests through gravity, inertia, and the expansion of time. Mass is not merely a number, it is the signature of the universe, the way every particle, every object, every energy field participates in the vast fabric we call reality. And perhaps most importantly, mass does not need to be fully explained for us to appreciate it. It exists in experience, in the rhythm of the planets, in the moment we feel Earth's gravity beneath our feet, in the way galaxies rotate around each other, in the way light bends through regions of empty space. It is a phenomenon, a behavior, a whisper among the components of the universe. And it is through mass that we sense the silent connection among all things, from the tiniest fundamental particle to the enormous structures of the cosmos. As we continue to explore, from dark matter to quantum gravity, from string theory to the Standard Model, mass remains an open mystery, a playground for imagination and scientific creativity. It reminds us that the universe is not a dry machine, but a living symphony, where every note, every rhythm, and every vibration contributes to wondrous harmony. Mass, thus, does not merely measure what we see, it is the way we perceive the rhythm of reality, an invitation to look deeper, to understand not just matter, but how the universe tells its own story. Mass is not merely weight or a number on a scale. It is a subtle presence, a silent force shaping the entire universe according to its own rhythm. When you place your hand on a table, feeling its heaviness, or when you walk on the ground, noticing your body seemingly drawn toward the center, you are touching a phenomenon deeper than what the senses directly reveal. Mass is the echo of fields, the dance of energy, the resonance between particles and the surrounding space. It is not a substance contained within, but a relationship, a manifestation of how every component of the universe interacts with one another. Even the seemingly empty space is not truly empty. Quantum vacuum, with its waves of energy constantly appearing and disappearing, contributes to mass in ways invisible to the naked eye. Every particle, every photon, even when massless, senses and responds to regions curved by other energies and masses. This is a reminder that emptiness is not truly nothing. It is a sea of potential, an invisible stage where forces and fields weave the rhythm of the cosmos. Mass is also a measure of time. We know that the heavier an object, the slower time passes around it. A clock near the surface of the Earth runs slower than a clock at a higher altitude, and this effect becomes extreme near the event horizon of a black hole. 1 hour near a black hole may correspond to centuries elsewhere. Mass and time are not separate entities. They intertwine in a space-time dance, where every motion, every force, and every field of energy interacts subtly. Because of mass, time is no longer uniform, but becomes a flexible, elastic, and dynamic phenomenon. The stars we see shining in the sky are vivid evidence of this interaction. Each star, with its enormous mass, shapes the flow of time and space around it, keeps planets in orbit, and contributes to the gravitational network connecting galaxies. Galaxies, while rotating, are reinforced by dark matter, an invisible but crucial component. Dark matter not only possesses mass, but also acts as an unseen glue holding the cosmic structure together, guiding the motion of stars and galaxy clusters, emphasizing that mass is not always tied to matter we can observe. On the microscopic level, quantum fields tell another equally wondrous story. Quarks are bound by the strong force. Electrons interact with the Higgs field to feel mass, and energy within particles continuously fluctuates, producing subtle vibrations that manifest as mass. It is an emergent phenomenon, a trace of complex and unceasing interactions. As particles move, collide, reflect, or absorb energy, mass is continually reaffirmed, silently and persistently. Mass is also an invitation to reflect on the philosophy of physics. It raises questions about the nature of reality. Is mass an intrinsic property or an illusion emerging from hidden complexity? It is an effective measure, a way that particles and fields negotiate with one another to create the sensation of heaviness we experience. Mass, in this view, is like a song, not an object, but a behavior, a subtle whisper of the universe, where every particle participates in the dance and every energy contributes to the overall rhythm. Imagine a distant galaxy where stars move around an invisible center, where orbits are shaped by the silent gravitational pull of dark matter. Photons from those stars, journeying across vast space, curve along invisible paths, carrying traces of mass they do not directly touch. This is proof that mass is a gentle, subtle pull, present everywhere, simultaneously creating structure and weaving the flow of time. Even our own bodies are part of this cosmic tapestry. The atoms in our bodies, every electron, proton, neutron, are not merely matter. They are anchor points in the universe, helping shape the space-time around us, participating in the larger story of energy and fields. Every step, every movement, every heartbeat is a sign of the continuous interaction between mass and space. Ultimately, mass is the link between the tangible and the intangible, between matter and time, between energy fields and existence. It is both phenomenon and behavior, both weight and rhythm, both measurement and narrative. When you look up at the sky, when you feel your hand on a chair or your feet on the ground, you are touching a part of that story, the story of mass, of force, of time, of the delicate and elegant interconnectedness of the universe. And it is precisely this complexity that creates the beauty of mass. It is not just a physical property, but also a philosophical experience. It teaches us that everything, from the tiniest speck of dust to the most distant stars, is held together by an invisible but perceptible force. It reminds us that familiarity always hides wonder, and awe does not need to be far away. It is right before our eyes, beneath our feet, in every step and every breath. Mass is connection, rhythm, the whisper of the universe that we are fortunate to hear, a song in which each of us is a note in the eternal symphony.